Okay, in the last lectures, we are discussing about the gate level modeling or structural modeling, or the switch level and transistor level modeling. Okay. So, normally this gate level modeling will be useful to describe the circuits consisting of fewer gates. Okay. For the large circuits or the complex circuits which contains several gates, it becomes difficult to model using the gate level. So, in that case we will go for this the data flow modeling. So, the next step of the modeling is called data flow modeling. I will call as DM. So, in case of gate level or structured modeling, we are going to use the keywords corresponding to the gates. So, whereas in data flow modeling, basically this data flow modeling uses a continuous assignments called as assign. So, this data flow modeling basically provides means of describing the circuit by logic function rather than gate structure. So, in case of gate level modeling, we are going to use the gate structure. So, this provides means of describing the circuit by means of a function, not the gate structure. Okay. So, here how does this will describe this circuit is? So, it basically uses the different operators. This data flow modeling uses different operators which acts on operands. To produce the desired results. So, basically this uses the different operators. So, in Verilog HDL, nearly 30 different operators are there, like this is binary addition. We have discussed these operators in the introduction class of this Verilog. This is binary addition. Similarly, this is binary subtraction. This is bitwise AND. And this is bitwise OR. And this is bitwise XOR. This is bitwise NOT. And this one is question mark followed by first is this is nothing but a condition. So, like this we have different operators which are nearly 30. Okay. So, how to express this assign statement? So, the assign statement uses continuous assignment. Normally, this data flow modeling uses continuous assignment. So, what is this continuous assignment? Okay. So, in continuous assignment, this is nothing but a statement which assigns a value to the net. So, what is net? We have already described in the introductory class of this Verilog. So, a net is nothing but net in Verilog represents a physical connection between the circuit elements. For example, if I take a AND gate with the two inputs A, B, output Y, if this Y is connected to some OR gate, if these are coming from some other AND gates, this is coming from some exclusive OR gate. So, the connection between the circuit elements, this AND gate and this AND gate is connected through this A. So, A is called as a net. Similarly, B will act as a net, Y will act as a net. So, basically a net is a physical connection between the circuit elements. Okay. So, how does this statement is formed? So, we are going to have some expression on the right hand side. So, if I take the example of this assignment, assign Y is equal to A and is represented by bitwise and is by this. So, whenever this right hand side is a expression, this is called normally Boolean expression. Which uses operators and operands. Okay. Here only one operator is there, AND operation, this is operator, and A and B are called operands. This is one operand, this is another operand. So, basically this right hand side RHS will be represented by a Boolean expression which uses operators on operands. Okay. So, whenever any operand changes, then the RHS is computed. That computed value is assigned to LHS, left hand side, this is Y, okay, using this assign statement. Okay. So, sometimes if I want to assign the computed value to the left hand side net, this is basically net, after some time. Okay. So, in that case we can use delay also. Okay. So, another example of this assignment through delay is, suppose if I write assign, this is the symbol for the delay which we have discussed in the earlier classes, 5. So, I want to assign after 5 milliseconds Y is equal to A and B. So, the difference between this assign and this assign is, here we have this delay extra. Okay. So, here in this case whenever A changes or B changes, this AND operation will be computed and that will be assigned to Y. Whereas, here whenever A changes or B changes, after 5 milliseconds this A and B will be assigned to Y. Okay. For example, if I take say A is something like this and B is something like this. If I assume that this is say 5, this is 10, 15, 20, 25, 30, 35 and so on. This is say milliseconds. Okay. This is A, this is B. Let us assume that they are at logic 0 from the infinity. Let us assume that they are coming from infinity with logic 0. Then what will be y? So, initially because these two are 0 from infinite, y is also 0, but at the point of 10, actually this is becoming 1, this is also already 1. So, output should be 1 because this is end operation. Okay. But here because of this 5 seconds delay, this 1 will be appeared at 15 seconds rather than 10 seconds. Here this becomes 1. Actually this 1 has been produced at this 10 seconds only. 10 seconds B is also logic 1, A is also logic 1. Output should be 1. But because of this 5 milliseconds delay, the output y becomes 1 at 15th second. Okay. Now this will continue up to 25 second, it should be 1 because both are 1s. So after 25th second output should go 0, but because of this 5 seconds delay it will go 0 at 30th second. So this will continue up to this one, and at 30th second it will go to the 0. So you see the difference between the direct assign and assign with delays. Okay. So basically in data flow modeling we basically uses the assign keyword. So I will give some other examples. So I will write the data flow modeling of a 2x1 multiplexer. So I have described this 2x1 multiplexer using the gate level modeling as well as circuit level modeling in the earlier lectures. Okay. So we know that this 2x1 multiplexer will have two inputs. Let us call the inputs as A, B, and there will be a selection line S, and there will be one output Y. So the operation is basically S, Y will be S0 means Y is A, S1 means Y is B. So the Boolean expression for this one is, so here we need the Boolean expression rather than the gate structure. As I have already discussed, in case of data flow modeling we need a Boolean expressions. So Y is given by S complement A plus S B. So how to write this data flow modeling? So initially we will define this as module. I will give the name as 2x1 mux under this one DF. DF stands for data flow modeling. There are 3 inputs and 1 output. Output Y, inputs are A, B and S. Output Y, inputs A and B, S. In case of gate level modeling you have to write down the gate structure. So you have to implement this using basically gates. Whereas in data flow modeling you have to write assign Y is equal to, this is S complement, this is S complement and A or is nothing but this one, this is the bitwise OR operation, then S AND with B, then AND module. This is relatively a simple modeling when compared with the gate level modeling. Okay. So I will take another example of decoder, 2x4 decoder. Using data flow modeling. So if I take the positive logic, so this 2x4 decoder will be thing like two inputs A and B, and we can have one more input called enable signal, and 4 outputs y0, y1, y2, y3. So, the operation is enable signal A B y3, y2, y1, y0. If enable is 0, regardless of A and B, none of the output will be selected. Selected means 1, not selected means 0. Okay. So, in order to select any one of these outputs, enable should be 1. So, for 0 0 y0 is selected, for 0 1 y1 is selected, for 1 0 y2 is selected, for 1 1 y3 is selected. This uses positive logic. We can design using negative logic also. Most of these ICs that are available uses negative logic, because negative logic circuit can be implemented by using the NAND gate. NAND gate is a universal gate. Okay. So, for the sake of simplicity, here I am using positive logic. This can be implemented by using AND gate. So, what are the Boolean expressions for y0? y0 is 1 here. So, these two are zeros, but E should be 1. So, this is E, A bar, B bar, y1 is E is common in all the expressions, A bar B, y2 is E, A B bar, y3 is E, A B. So, you can write down the Verilog code correspond to this decoder. Basically, here we have AND gates. Okay. Module. So, you have to give 2 by 4 decoder underscore DF data flow modeling. So, basically we have 4 inputs and 1 enable input and 4 outputs, Y output, and there are enable input and X is the another input. Of course, X and Y are vectors here, later I am going to define that. Okay. So, output 3:0 Y. So, we have Y3 to Y0. Okay. Input 2 only, we have AB, sorry, what are the inputs that we have written is AB. This input is not X, this is AB. So, input AB. Then we know that the expression for Y0 is E, A bar, B bar. So, assign Y is 0. This is y0 because this is vector y3, y0, y1, y2. So, y0 is equal to E and not operation with A and not operation with B. Similarly, you can write assign y1 is equal to E and with A bar and with B. Assign y2 is equal to E and with A and with B bar. Assign y3 is equal to E and with both A and B and module. This is the data flow modeling of a 2 by 4 decoder if I use the positive logic. Here instead of using this 4 assigns, we can write this alternatively as a single assign also. So, this you can replace it with a single assign you can write y 0 is equal to E and with A not A and with not B. Now, we have to put a comma, then y 1 for single assign you have to put a comma here, y 1 is equal to this expression, y 2 is this, y 2 is comma, and write otherwise E and not A and B comma y 2 is equal to E and A and not B comma y 3 is equal to E and A and B. Now, we have to write the filters. So, is another way to write this, you instead of using 4 assigns you can use a single assign. In that case you have to separate this using comma symbol. Okay. So, this is the data flow modeling of a 2/4 decoder, which basically uses the AND gate, but normal decoders if I take, which are available in the IC form, if I take LS 74138 which is 3 to 8 decoder. So, here the signals will be active low signals. Okay. So, here the signals A, B will be available as active low signals, A, B, enable also active low signal, output also active low outputs. This will be available as y 0 bar, y 1 bar, this is also E bar, y 2 bar, y 3 bar. So, this type of circuit can be implemented by using NAND gates. So, similarly, you can write this Verilog code for the negative logic circuit which uses the NAND gates. Okay. Then I will take another example of adder. I will start with the half adder, I will go up to the look ahead carry adder. Okay. So, if I take half adder using data flow modeling. So, we know that half adder circuitry will have 2 inputs x and y and 2 outputs sum and carry. This is sum, this is carry. Okay. So, module half adder underscore data flow S C X Y output S comma C input X comma Y. Assign S is equal to X exclusive R, symbol is this, operator Y. Assign, you can use a single assign and you can put a comma also. Okay. Carry is equal to X and Y. This is one way to write this Verilog code in data flow modeling. So, another concept is we can have concatenate this is a principle called concatenation. This can be applied on scalars as well as vectors. If you want to use this concatenation, So, this instead of having 2 assigns, so we can replace these 2 assigns with single assign, and this concatenation has to be represented by braces. Output is carry and sum is equal to, the inputs are x plus y. So, this will assign, this will basically perform the binary addition, this is addition. Here we do not use this symbols like binary operators. Okay. So, this is binary addition basically, it will perform all the combinations, say 0 plus 0, result is 0. Okay. So, 0 plus 1, this is, if I want to write 2 bit equivalent of this one, this is 0 0, sum and carry, or if I write this carry and sum in the same order, 0 plus 1 is sum is 1, carry is 0, 1 plus 0 is carry is 0, sum is 1, 1 plus 1 is carry is 1, sum is 0. So, in the order that they will generate, this is MSB, this is LSB. So, after this addition, whatever this LSB bit is assigned to this sum and MSB bit is assigned to C. Okay. So, this is what the concept of concatenation. Okay. We can apply for scalars as well as the vectors. Okay. So, this here x and y are scalars, they are single bit numbers. Okay. Later we are going to apply the same principle on the parallel adders also. Okay. So, this is about the half adder. We can write in 2 ways, we can use either assign or we can concatenate using a single assign. Okay. Then full adder. I will write directly concatenation. Okay. So, the full adder is basically we have 3 inputs, this is full adder. Here in case of data flow modeling, we do not need the internal circuitry, if I know the function, that is enough. So, this basically we have 3 inputs, this is x, y, c in, if I call c suffix in, sum and carry out, 2 outputs. Okay. So, the expression for sum is x exclusive or y exclusive or c in, carry out is x y plus y c in plus x c in. We can write in 2 ways similar to the previous half adder, module full adder underscore data flow modeling, you have c out x y c in, output s comma c out, input x comma y comma c in. First I will write using the multiple assign statements, assign sum is equal to x exclusive or y exclusive or c in, assign carry is equal to x and y or y and c in or x and c in. You can write overall another bracket this, then end module. This is without concatenation. Okay. Now, if I use concatenation, so these 2 assigned statements can be changed to single assign statement. So, MSB here is carry C out comma S is equal to x plus y plus C in. Basically, this will perform the addition of the 3 bits. Okay. So, in that MSB bit will be assigned to C out, LSB will be assigned to S. This will take all the 8 combinations. The MSB bit, so 0 plus 0 plus 0 is decimal 0. Okay. So, 0 plus 1 is decimal 1, 0 plus 1 plus 0 is also decimal 1, 0 plus 1 plus 1 is decimal 2. So, these decimal values will be represented by 2 bit binary equivalent. Okay. This is correspond to 0 0, this is correspond to 0 1, this is correspond to 0 1, this is 1 0. So, in that this MSB bit is assigned to C out and LSB is assigned to sum. So, we know that in case of 0 plus 1 plus 1, the sum bit is 0, carry bit is 1. So, like that 1 plus 1 plus 1 is 3. In case of decimal, the binary equivalent is 1 1. So, both will be assigned 1 1. Okay. So, like that this concatenation of this vectors or scalars will be very much useful in the data flow modeling to simplify the code. Okay. So, now the next one is we have 4 bit ripple carry adder. If you want to write the codes using the gate level modeling, you have to instantiate the previous programs, like you write the first code for half adder, you instantiate twice that in the full adder, and you have to instantiate 4 times that full adder into the 4 bit ripple carry adder that we have discussed in the earlier lectures, whereas here that is not required. Okay. So, we know that in case of 4 bit ripple carry adder, we have 4 full adders. So, we know that 4 full adder will have 3 inputs and 2 outputs. These are this LSB inputs. Let us call this one as A0, B0, and this is say C0, this is C1, this is C2, this is C3, this is C4. You can also call as C out. This will give sum bit S0, S1, S2, S3. This is A1, B1, A2, B2, A3, B3. This is ripple carry error. Okay. So, in order to write this code, we can use the concatenation principle. So, module ripple carry adder underscore data flow modeling. So, the outputs are C4, S, inputs are A, B, C0. Of course, A, B and some are here vectors. Okay, I am going to define in the next keywords. Output C4 comma 320 S. This is S3, S2, S1, S0. Input C0, 320 A and B. Both A, B are 4 bit numbers. Okay. I will write directly this concatenation of these outputs. Okay. Assign. So, what is the MSB bit? Total result is 5 bits. So, in this 5 bit result, this is LSB and this C4 is MSB. If you add two 4 bit numbers, so the resultant can be 5 bits, because we are adding two 4 bit numbers, the maximum number is 1111, 1111. If I perform this addition, 1 plus 1 is 1 0, 1 plus 1 plus 1 is 1 1, 1 plus 1 plus 1 is 1 1, 1 plus 1 plus 1 is 1 1. So, we will get at the most 5 bits. So, this represents C4, this represents S0, this is S1, S2, S3, okay. This is S0, S1, S3 and this is C4. Okay. So, in this MSB is C4, assign C4 comma LSB is S0, or you can simply write S also. Okay. S0. So, what is that? Is simply A plus B plus C0. So, this A will take 4 bit number, this will take 4 bit number, this is 1 bit number. Okay. So, then among these 5 bits S0 will be assigned, this least significant bit is assigned to S. We can also simply write S also here, this represents already inside this S. So, S is nothing but S3, S2, S1, S0. So, LSB bit is assigned to LSB, the next LSB is assigned to S1, so on, MSB is assigned to C4. Okay. Then we have end module. This is the beauty of the concatenation. Okay. And we can extend this to the look ahead carry adder. Okay. So, as the number of stages increases, if you want to add two 4 bit numbers, what is the maximum propagation delay? Because this carry has to ripple through the adders, that is why the name ripple carry adder. So, from C0, C1 is generated, C1 again it will propagate to C2 in a ripple manner, that is why the name ripple carry. So, what is the total propagation delay to get the final output? If I take the same, the worst case principle of this 1 1 1 1, here we will get a carry, here we will get a carry, here we will get a carry, here we will get a carry. Okay. This is the worst case propagation delay is 4 times the propagation delay of each full adder. If I want in general n bit ripple carry adder, the total worst case propagation delay is n times the propagation delay of full adder. As the number of stages increases, the propagation delay also increases. Okay. So, to avoid this, regardless of the number of stages, if we want to have a constant propagation delay, we have to go for carry look ahead adder. So, we will discuss this carry look ahead adder in the next lecture, and we will write down this data flow modeling using this concatenation principle. Okay. Thank you.